in those statistics, ooh, look at that. It's not cold enough now. Let's see if it will do it on its own. I don't know if it will levitate on its own once it gets cold enough. Does it need more? But anyways, so you guys will see. Oh, look at it go. No way. Very interesting. Take a guess at what that is. It's a lump of coal for you for Christmas. Close. Is it the fragment of my dead heart? No. You're getting there. You're getting there. My heart's not dead. It is not my soul. It's not my soul. I4T, welcome to the channel. Thank you for the follow. It is not a kidney stone, but you guys are both very close. Because so the Meissner effect is actually a quantum phenomenon. Although it seems kind of, it seems classical. And we've talked about things like at a classical level quite frequently. When we've talked about this stuff in the past. The mathematics cries in theoretical physics. Yeah, only because the math is quite complicated if you want to consider quantum effects, which we do. We do want to consider quantum effects. All right. Let's pour some of this into here. Not over my pants.
Boo-hoo is too hard. I can't do the math.
I gotta watch it. I wasn't paying attention. Okay. Good, 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 good. Okay. So what we have here is actually a superconductor. Okay? So you guys were all close by like Eric's heart. Oh man, it's getting on my pants.
Welcome to the Physics with No Math stream.
Oh, come on. We're going to talk about the phenomenon. Jeez. Man, you guys are harsh. Don't let the hydrogen, the liquid nitrogen, excuse me, hit you in the pants. Could make for some sad thighs. Ready? Superconductor for a project. A friend of mine bought one in high school for a chemistry project. Yeah, you can actually make them. It's not too difficult to like make this. Put it back. Right on there. Ooh, look at that mist. We're going to pour this back into here. And then we're going to dump this all over it. Ready? Uh-oh, uh-oh, uh-oh. Ooh, ooh. There we go. Ha. Ha. Look at it, now it's so misty. Hurts a lot. I think this amazing life lessons. Don't let the liquid nitrogen hit you on the legs. Is it the Meissner effect? Yeah, the Meissner effect. I don't know how you say it. It's spelled M-E-I-S-S-N-E-R. Ready? Let's see if it's cool enough. Oh, no way, dude. No way. Look at that. Let's take a closer look, shall we? Meissner. There it is. Ooh, quantum levitation. Uh-oh. I dropped it in. So yeah, so there's nothing underneath it. In fact, just to show you certainly, it is completely levitating. See? Yeah, there's nothing underneath it. Now my turn to levitate. Okay, hold on. Let me get on top of the superconductor. Hold on. Or we could do another one, too. Hold on. How about a disc? Ready? Shing, shing, shing. Ooh.
Make it spin.
Make it spin. Man, you guys are demanding. You're going to hear kind of like a common classical explanation of this with eddy currents. And now eddy currents are something that is basically a product of changing a magnetic flux So the way that we did that, the way
I
that we
won't
showed that.
understand anything about how it works with no math.
Is this live? This is live. No, this is live. Look at, ready? Hello, hello. Here, I'll do this too. No video. Howdy. See? Watch, ready? Poke, poke, poke. Fully live. And what the eddy currents do inside of what we showed. There we go. I kind of got it spinning a little bit. Here, let me see if I can turn it. I got it spinning now. Can you see it spinning? That's so cool. Okay, so when we talked about eddy currents, we talked about how if you take a magnet and you move it through a tube, like an aluminum tube or a copper tube works the best, then when the magnet is falling, there's a magnetic flux, right? And the magnetic flux, basically, and magnetic flux is a change in magnetic flux, is what I should say. Magnetic flux being a magnetic field going through an object, right? Any magnetic field going through a certain area is the magnetic flux. And as the magnetic flux changes, you're going to generate a new magnetic field, right? And it's going to go the opposite direction, right? So then the idea is this magnetic field generated in the opposite direction is trying to fight the change in the magnetic flux. So the amount of magnetic field going through an area, if it's changing, nature doesn't like that. Nature tries to stop that from happening. So what people thought for a while was that, hey, like now there's no magnet here, but if I put the magnet here, then all of a sudden the system's unhappy because they're like, well, I don't want there to be a magnet there because I was happy with no magnet. So they thought that what was happening is you got these surface currents on the top of this piece of conducting material, right? And the superconductivity means that all of the resistances are lowered in the object, right? So with lowered conductivity, with lower resistance, the eddy currents, the small currents that are being generated, you would think that they would be able to be more powerful, and that's true. But what's required for these currents is a change in magnetic flux. Here I just set the magnet there. It's not moving or changing or anything, right? It's just there. This liquid that I put in is liquid nitrogen. It runs incredibly cold because you want your superconductor to be below a certain temperature, which we'll talk about in a second as well. So you want the superconductor to be below a certain temperature. Are you an alien teaching us about UFOs? Yes. Oops, lost it again. Hold on. Yeah, so what they thought was that, hey, if I introduce a magnetic field, it's going to generate these currents, and since there's little to no resistance inside a superconductor, then that must mean that the eddy currents are just strong enough to generate a magnetic field that would be repulsive to the magnetic field that is generated by the magnet, right? Hence making it levitate, okay? But what was actually true is that the way that the superconductors work was you had to lower them to a certain point for this to work. Like if you had a superconductor that wasn't at a low temperature, let's see if I can get a couple here. We do have some issues with these working properly, but let's see if I can get one to work here. So we'll take another superconductor, and these are homemade superconductors that the lab coordinator at Binghamton made. Let's see if I can make it work. Which you can make it up, you can look up recipes. So if we were to take this superconductor right here, and just get my fat thumb out of the way here, and just set the magnet on, nothing happens, right? It just sits on there. It's not levitating, right? You guys can just see it just sits on there, right? But now what we'll do is we'll take it and we'll supercool it. But what they found out was basically that if you lower the temperature, now if you guys want to see, you can see it bubbling. Those bubbles indicate that it is still, that it's just coming down to the right temperature. If I can, ooh. Okay, we're not gonna play with it. I don't want to screw up the camera angle. Okay, so the Yeah, so what they found out was that it wasn't just a gradual thing. Like it wasn't just like as you lower the temperature, there's it just gets more and more repulsive. What they found out was that there's a hard cutoff, right? That there is a critical temperature is what it's called. And at that critical temperature is when things start to get very interesting, right? That's when this phenomenon starts to happen, where you get this perfect solid current. So they knew this current that almost zero resistivity, which means you get really strong surface currents. Now notice I'm calling them surface currents now and not eddy currents, because what they found out was that they're not in fact the eddy currents from the change in magnetic flux, simply because, like I showed you, I could just put that one stationary object on, and it was not moving, and yet it was still getting repulsed, right? Okay, so let's see here. Let's see if this object is cold enough now. So let's move it back. So remember, we tried it, and it showed that it was not. Just gonna do that. We showed that it just did not repulse from it, but now let's see here. Ooh, it wants to. Hold on. I'll have to. It's not level. This might be interesting. It wants to slide down it because it's not level. There you go. So you can see that it is slightly levitating above it. Let's use the little magnet though. But anyway, so what they found out was that there's a hard cutoff, a critical temperature, which this happens. So now, because the magnet's not moving, it's not a change in flux, and because you can kind of see it there. Oh, that looks weird. That looks like I'm balancing it on the corner. That looks cool. Let's see if I can get it nice and, hold on, focused. Like one of those rock balancers. So, yeah, so they found out, so the critical temperature was the temperature at which this effect happened, and they found out that it was not due to these changing magnetic flux, because the magnetic field is not really changing. So, here's what they did. They thought, okay, this has to be a quantum effect. Now, inside the realm of quantum mechanics and particle physics, there's a thing that I studied quite a lot, which was called statistics. So you have fermions and bosons. Those are the two types of elementary particles that you have. And in those statistics, ooh, look at that. It's not cold enough now. Let's see if it will do it on its own. I don't know if it will levitate on its own once it gets cold enough. Does it need more? But anyways, so you guys will see. Oh, look at it go. No way. That's pretty cool. Let's make sure it gets colder and colder. Yeah, look at that. It does levitate on its own. UFO confirmed. So that's cool. So now you got to see it in action, because that was below. So this superconductor was actually above the critical temperature when I did that, when I took it off and put it on the desk, and then when I put it back on, you could see that it went below its critical temperature and began doing the repulsive stuff again. So now you can just set it up there. So basically what we have is the energy, the fermions, below certain temperatures, fermions, this is called BCS theory, fermions can bunch up into pairs. Now fermions have spin 1/2 and bosons have integer spin. So the integer spin versus spin 1/2. So if you take two fermions and you put them in a state together, in a ground state together, where one is spin up and one is spin down, or I should say a state together, not a ground state. A state together, it looks like the fermions look like bosons, right? And that was interesting because if there was fermions in pairs, you could actually lower it enough to get the pairs, these pairs are called Cooper pairs, that the actual would fall into a lower ground state as a pair. And what they found out was this lower ground state is, it is possible to have these currents happen at the lower ground state. Those are the surface currents that are repelling this, is from the Cooper pairs losing, and because basically the resistance is going to be the interactions of the fermions with themselves or with the atoms in the lattice, right? And if the fermions act as a boson in the Cooper pairs, then the interactions virtually go away and it becomes resistance free. So that's where these currents come from. Now I want to see a black hole singularity in your office. Work on it. Is there any resistance when you lift it up while it's floating? No, none at all. Nope. It's very, very... No resistance. So there's one of these demonstrations that's done with a Mobius strip. And a Mobius strip is a lot like the cup trick, where like if you go around once in the cup trick, you get a weird image. I'll show you guys the cup trick in a second. If you go around
together because there is no math to separate them.
Throw some liquid nitrogen on the floor. We can do that in a second. Here, let me do this. Ooh, should I do the cup trick with liquid nitrogen? I'm all out. I think I have more over there, but I'm not going to do it anyways because it's dangerous. So the cup trick is basically like this, right? You take the cup, and if you do one full rotation, so we want to get the cup back to here. So if it's what we call a boson integer spin, so integer spin, boson spin, if you go around 2 pi, then you come back around, you get like that, right? Or you can just spin it like this. Either way, it doesn't really matter. Okay? So that's spinning it one way. So that's one type of rotation. Another type of rotation, and this is what we show as like analogous to like fermionic spin, is if you spin it around once and come back, look at now everything's kind of crooked. Like right, my arm is not right. My arm is different. But the cup has gone around one full rotation, right? But if we, and so let's go back around, ready? So if we go around once, like that, but if we go around a second time, we're back to the way it should have been, right? So around once, we have this weird shape, this crooked different thing. So we say this is analogous to integer spin, because integer spin, if you want a state to look the same, you have to go around twice. So you have to rotate it twice to get back to the same state. Now, that means, so the fermions and bosons are just inherently different, right? And this is one of the things that ends up going a lot into the quantum levitation. So paired electrons act as force carriers. I don't know if I'd say they act as force carriers. Yeah, well, okay, so kind of. In the sense that bosons are force carriers, yeah. Yeah, and what happened is, actually, that's a good point. If you have Z, not the letter, the author. Do you have Z? Quantum field theory in a nutshell. His description of this is actually like that. So it turned out that what Landau and Ginzburg did was they basically modeled it like a field that looked somewhat like a force, I think. Maybe a force carrier, I should say. Maybe Justin would know a little bit better, but you don't. Let's see what it says. With brilliant insight, Landau and Ginzburg realized that without having to know a detailed mechanism driving the pairing of electrons into bosons, they could understand a great deal about superconductivity by studying a field phi associated with these condensing bosons. So yeah, they treated the field just like a boson. And they did that, and they were able to find where the Meissner effect came from. That's a big nutshell. Yes, it is. But this is the Meissner effect. It's basically like these currents are generated because of the because of the way that the fermions behave. They lower to a different ground state, and there's and they basically repulse any magnetic field that gets close to it. And they will literally knock it away completely. If you spin the superconductor, will it generate a magnetic field? No. That's a good question. So I think a superconductor should still be uncharged. So I guess maybe in this apparatus it would have to, right? Because right now, is it generating some sort of charge? Well, it's generating surface charges, but they probably all cancel out. So a charged object that spins will generate a magnetic field, right? But I don't know. It's called a magnetic moment. But I don't know, since they're surface charges, they're all, or surface currents, they're going to be equal and without. So I don't think that this is going to be, okay, it's going with the music. I don't think this is going to be one of those situations where if you spin it, it will actually have a magnetic field. But I don't know. This could be used against Magneto, maybe. Just, you know, make him levitate. And then he's stuck. So what do you guys think? I heard that if you spin a superconductor, it generates a magnetic field. It's called the London moment. Maybe. Is that the one that's like, let me see what, no, I don't know. Let me see. There's so the London equation and the
Magneto carries liquid nitrogen inside his pants.
how the old Indians worked. They used spinning liquid mercury that kept feeding current into it to make magnetic field bigger and bigger. Interesting. No, I've never heard of that. Let's see the London moment. Quantum mechanical phenomenon whereby spinning a superconductor can generate a magnetic field whose axis lines up with this exactly with the spin axis. Interesting. Any superconductor caused by electrons lagging behind the rotation of the object. There it is. Interesting, interesting, interesting. That's pretty cool. It's perfect diametric, so it would repulse Magneto. Explains why UFOs crash a lot in the natural land. Yes, explains why UFOs crash a lot. True. True, true. The London moment is what brought down the London Bridge. I did not know that. Also, don't believe you. But, you know. Cool. Seems to only be repulsive.
Draw the FBD.
Draw the free body diagram. Yeah, I feel like it would do nothing, right? Like there's only a magnetic field is only pushing this enough to keep it away. You know what I'm saying? Like it's not going to launch it in a different direction. So I feel like it would be basically like you would push the two together. I'm losing some temperature on it now. You would push the two together. Oops. And that would be it. It would just keep it away enough so it wasn't. So the way that it works is there is what's called a penetration something. Maybe London penetration? Let me see here. It's called London penetration length. And it's basically like, it's not as dramatic as I made it sound out earlier. There is a penetration length to how much the magnetic field will go in based off the temperature. And so I imagine, see we're losing some superconductivity. I'm going to see if I have any more liquid nitrogen. Hold on. So there is some sense that it's, you know, it's partially controlled by the way that the magnetic fields are interacting. And there is a surface level of the, man, I have so much more liquid nitrogen than I remember. There is some level of the surface that is, you know, is being penetrated by the magnetic field. It's a very, very small level, but there is some level of it. Let's see here. With no gravity, it would push it away forever. No. I mean, I guess if you made them kiss, then yeah, it would push them away forever. But if you were just like throwing something close to it, it wouldn't. It would probably have that same thing that would happen. You know that, do you know that one phenomenon that we talked about where, hold on, I gotta move my stuff away from here. Where if you took a big piece of copper, right, and also took a magnet on a pendulum, and you let the pendulum go, and the copper or the magnet would swing close to the pendulum, right? Okay, so we're gonna watch it take off here. And you swing the magnet close to the copper. What would happen is it would come really close and just sort of dead stop without touching the copper, because again, like you're introducing so much magnetic flux and change in magnetic flux that the currents are strong enough to just stop it at a certain point. Would it reverse with heat introduction? Yeah. Like, so it would go back down if you were to introduce heat to the superconductor, for sure. Because the temperature, it's basically like the resistance is really low because of the because you get these Cooper pairs from fermions dropping into this lower state, right? Otherwise, you're not going to get that low of resistance and get the surface currents. Has it given up? Oh, no. I did it for it. Oh, thanks, Justin. I appreciate it. Geometry scammers? I know. They're always coming after us. Don't drink the liquid nitrogen. But anyways, isn't that cool? So that's the Meissner effect. It is a quantum mechanical effect. It has to do with fermions behaving like bosons. Very, very cool. Low resistance, but
You are
high
the source of my
fun.
surface tension.
Yeah? What about surface currents? Am I the source of your surface currents, too? When you turn the superconductor upside down, it still keeps the object in the same position. It would work the same outside of gravity. Cool.
Just
The
the tension you
Mobius
needed.
strips are very cool too because like so the Mobius strip, like I said, I didn't finish the story. Like if you took that cup and you spin it around once, that's like a Mobius strip. If you go around once in the Mobius strip, you end up on the bottom. So what they do is they make these, right? They make these in such a way that if you were to put this on the top of a magnetic track, so if this was a superconductor, right? So this is a superconductor. If you were to take this and put it on top of a magnetic track that is a Mobius strip and zoom it around the track, it's not going to like leave the track. It's going to follow the track, although not like that. It's going to follow the track. And if it gets to the part where the track spins, the puck will stay attached but to the bottom of it. And then it will zip around the bottom of it, and then it will flip back around and come up to the top again, and then zip around and go around the bottom and then come back up to the top. It's really cool. And you can look these up on YouTube and stuff.